Okay, let's start with the last presentation. Now we go to another very specific application. Paul is from C++. You will see that it was mentioned also during the first presentation by Peter, the first day. They are the team that win the Google Challenge box. So the one that they were able to make the most compact, the most powerful, the most efficient, and the most reliable converter, okay? And you will see all the story by Paul, so I'm really looking to see your presentation. Let's go, Paul.
Thank you, Gaudenzio. So the last, and I hope not the least, presentation. So I am the R&D manager from C++ since 20 years now. And really this experience of power electronics is really challenging every day and interesting because there is always something to learn in our business. So I heard that most of you are power electronics engineer. Is that true? Yes? I saw many hands up.
Some are on device engineer,
okay.
Other are power circuit.
So for this engineer, good news, you are not waiting for a long time to have a job. We are looking for, if you need a job, please address to me. And you can go to, yes. Now.
Do you think we can pack in this little box the power of this 2 kilowatt inverter? Well, our engineers did it.
The Little Box Challenge is an open competition initiated by Google and IEEE in July 2014. And what Google wants is to build an inverter with the highest power density. The minimum requirement is about less than half a liter. Today, a 2 kVA inverter, solar inverter, is about the size of a picnic cooler. So the challenge is to build an inverter roughly 10 times smaller than what is present on the market today. C++ Power manufactures modular inverters. Our challenge those last 30 years is to reduce the size of our product, have our product more efficient. Today, the best inverters of C++ is about 4 liters. And our customers cannot afford any interruptions. So the applications of our product is to secure their critical applications in the telecommunications, in the industry, in the data centers, and power utility.
We realized from the beginning that the project was completely new, completely different from what we did before. And so for that reason, we had to change the methodology to address it. We decided to first start with an internal team to develop the inverter itself. Aside to that part of the project, there is also mechanical, thermal, and different things that we are not really specialists of. And so we decided to find a local partner like Ceres, like Macrosys, like University of Liège. With that help, we finally get the result we really want to get. I mean, a small box and a very good inverter inside.
For the hardware, obviously, we did everything very small. For semiconductor, we choose new nitride of gallium. And for thermal aspect, we optimize honeycomb heating. Also, for storage energy, we decide to use new ceramic capacitor that use also for thermal dissipation.
Concerning the EMC filter, because of the reduction of the size, we needed to implement a specific customized shielding. In order to save time, we asked our partners to make a lot of simulations for us. Electronic simulation, but also thermal simulation. As an example, we tested several types of heatsink in order to choose the best one. It turned out it was the honeycomb model.
As far as software is concerned, we had to develop new control strategies to control the new components, and that was quite difficult. If we want to reduce the size of an inverter, we have to do a lot of calculation very fast with a limited processing power, so we had to optimize all the algorithms.
The time frame was by September 2014 to be registered as a team. So we were registered among 2,000 teams. Then by July 2015 to deliver a technical report and a testing report, which we delivered 5 days prior to the date. In September 2015, we were officially announced being part of the 18 finalists by Google, and we were invited by October 2015 to present and deliver the prototype in the InRel laboratory in Colorado. We were very impressed by the presentations of the other participants, but we are very confident about the result of the challenge for C++. Well, early in February, Google called us to notify that we were part of the last 405 who succeeded to pass all the tests, and invited us in Washington, February 29, to participate to the ARPA-E Summit, where the winner was announced. We were very surprised and happy to learn that we won. This really demonstrates the leadership that we are having in power conversion in the industry. It is a clear indication of our ambitions and how our know-how will serve our customer in the future.
As an engineer, it was very interesting to have the opportunity to work on that project. We had to make a new inverter from scratch, and that was very exciting.
It was a personal challenge to be within the 18 finalists. It was really great to work with the team. Everybody was enthusiastic to work.
It was a great challenge, and we already noticed that we use some of the techniques that have been developed in the Little Box Challenge in the product that we will release shortly.
So, that gives a good overall of the story and of the company. And just to remind what was the specification at the origin of the project, we had this GaN implementation, which is, let's say, an assumption. 95% efficiency weighted, so was the minimum efficiency. AMC class B means that the RF noise in the range frequency between 150 kilohertz and 30 megahertz had to be under 1 millivolt. DC voltage ripple at 100 hertz less than the 0.1 volt. And the maximum temperature on the enclosure should be less than 60 degrees. And the original volume suggested by Google was 600 centimeter cube. That was the challenge at the origin. And so, to achieve that, we had to develop different things. And at this time on the market, there were no driver able to sustain or to meet the high DVDT created by the GaN itself. So you know that this DVDT could rise a very high value, like more than 100. It's not 100 volt, but it's it's volt per nanosecond. So usually we use microseconds, so it's 100 kVA per microsecond. And a normal driver, for example, can meet 50 kVA. So it's not enough to drive a GaN. So we were not able to buy a driver on the market at this time to drive the GaN. The second thing is we had to make the volume as small as possible, and so that means we had to use active filter and also multi-layer ceramic capacitor for storage. Other things was to reduce the AMC filter. We will see what is it later on. And so we had to use the soft switching, 0 volts switching actually. We, by assumption, had to develop a current output limitation, because we know that per experience an inverter without current limitation is a nightmare. You never know what you have as a load, even during test. If it is defined at the moment of switching, you can have capacitive effect and things like that, so overcurrent. And so it's more likely that why the Fraunhofer, which was before us in the top list, has failed at 90 hours. They said it's only a wire, but we didn't see any current limitation in their design. High-speed current measurement is also a challenge when you use GaN, because we will see that we reduce the size of inductor to go into ZVS mode. And so the time to measure the current is very short. So there were also new things on that measurement way. You have seen that we use a honeycomb thanks to the nature to inspire us to find a solution to have a very high and density heat sinks. We had also to be very creative in the layer approach of the PCB, so we call it sandwich. It's really that. And also we have a shielded third or fourth order for the filter in differential mode and in especially in common mode. So that is the topology we have used, and so I will start to comment it. I don't know where is the laser. Okay, red button. So here you find the 5 leg is a half bridge. If you are power electronics, you know it. So there are 2 in parallel for the neutral point and 2 in parallel for the phase point, phase line. And the last leg is actually an active filter. You see that it's connected to a small capacitor, and actually there is about half the power that is transiting in that half leg. So it's the 2 kilowatt device. So in the filter, active filter, there were about 1 kVA going through that active filter. So I told you about the filter order. So here you have a first differential filter, and we put the same for the paralleling the device. It's not so easy to parallel to set in parallel the 2 leg of GaN half bridge, and so we decide to put some coupling inductors in order to help the paralleling operation. After that, we start with the common mode. As if you see common mode, we have 1 cell here. After that, we have another one here, and you have still another one here. Moreover, we have to add different shielding in orange. You have AMC earth shielding, and also here earth connection shielding. So without all these things, we were not able to meet this famous Class B requirement. So it's very interesting to use GaN, but the filtering is really a challenge each time you implement a GaN. As said Kyle before, he mentioned the DVDT problem with wire, but it's also a problem with a filter. What else to say about that? Maybe some question? No? Okay. So I told about ZVS, so 0 volt switching and phase shift. Here we can find different level of duty cycle. For example, here 75% on the line L and 25%. It's called centered PWM control. And you see that when the voltage is equal after a certain time, because the output inductor is small, finally the current is going to 0, and so you can go to 0 volt switch also. So same for different level of duty cycle in the system. So sandwich and the size of GaN compared to the IGBT is not only for the size that they implement GaN die in so small package. It's mainly also for the inductive leads. Okay, you can have today. You can buy if you want such GaN with normal package, but you lose a lot. You have extra losses due to the inductive leads and connection of the. If you don't use this kind of small package, if you use, for example, the same IGBT package here with a long lead, you will have extra losses which you cannot eliminate easily. So in order to reach this high density power, we had also to eliminate the usual electrolytic capacitor because it's too big. And same for, let's say, toroidal core, which is too big compared to IEEE model or ferrite model. And so same for ceramic multilayer, we have to use it even in an array. And some of them are even vertical between two PCB in order to use the ceramic capacitor as a heat sink also. Other things that we are to simulate is the magnetics of the all the magnetics of this inverter. And here is the output inductor. And so here you can find a 2D representation of the inductance, output inductance, with the let's say repartition of density of current in the wires. It's Leeds wire, obviously, at this frequency. We work between 100 kilo and 350 kilohertz. So at this frequency, you have a skin effect for sure, and proximity effect also. So a lot of simulation we have done for that project. Another type of simulation is only the circuit simulation, where we had to find the working condition for the switches. Thermal simulation also to evaluate the enclosure temperature. Also flow air simulation to evaluate which was the best heat sinks. Mechanical 3D simulation also to make this sandwich layer arrangement, and it was really a nightmare to put everything in this so small box. For example, we didn't have any leads inside, any wires. We put spring between the board in order to have contact. So it's very special to work like that. So at the end, we got this kind of, let's say, power density. That means 2 kilowatt in 220 centimeters cubic means that about 9 kilowatt per liter. It's probably the most power dense, highest power density in the world for an inverter, but it's also the most expensive one. So it's like, as I said always, it's like a Formula One. No? You have very good result, but it takes time to put it in the industry level. Okay. So to do that, we have joined the project of Gaudencio and several companies that you have heard this last days. And so we decide to work on, let's say, reliability of the GaN. And so here we are entering in our business. And so we just have released a new product, which is called Energy Router. And inside this product, we have three main converters. One is AC-DC, so you have an AC input here. One is DC-DC to go to a buffering, which is a quite big capacitor. And you have a DC-AC to go to the output. Over that, you have control with redundant communication between. You can parallelize this module. So that is one module of 3 kVA, where you can make flowing the energy from any port to any other one. So it's a bidirectional on each power ports. So if you want, for example, to put a PV panel here and reinject on the grid, you can do. And if you want to take the maximum power from your PV and put it on your loads and take the difference on the grid, it's also possible. So you can, let's say, consider these two ports as input and this one as an output. And you can, for example, take 40% on the AC grid and 60% on the DC. So that is what we have patented some years ago. It's the same configuration that we have in the previous slides. And so, as I said, there is grid input, an output, and a DC battery normally, or a DC source. Now, this is based on a 3-leg, and we are currently, these 3 legs are working in different modes. The entry, for example, is connected to a source, voltage source, so it is working as a current source. the output and the neutral are working as voltage source. So we have different control. The neutral loop, the neutral connection is having a trapezoidal, let's say PWM evolution, while the L output, so the output connection is having this kind of waveform, and if you make the sum of both, you have a perfect sinus. So our goals in this project 2020 is to first test the reliability on the real application, and so we are going also to compare different type of GaN cascode and E-mode versus maybe what we have today. I mean IGBT, and even we are going to test also SiC here, and so we will have a different type of, let's say, demo board in order to make reliability test in real site and real condition. So to do that, we will, as said Kale before, we will make small batch of 10 pieces of different board, and we will make it at higher stress, and it will be implemented next year. So to achieve that, we also had the support of onsemi that has made a prototype, virtual prototyping approach. And so what is important in our three-leg system is that we have two mixed mode of operation. I mean, a part of the sinus we are working in hard switching, and the other part of the sinus we are working in soft switching. To achieve that, our engineer makes SPICE simulation to provide the condition, the boundary condition or working condition on each switch, and onsemi has made the model of the switch and have on different point of the sinus, they have, let's say, cumulated for each working condition, they have cumulated the efficiency and losses on different devices. So they had this conclusion that conduction losses between E-mode and cascode was almost the same. The E-mode again show lower switching losses. Also, they have some advantages on the QoSS. I don't remember what is the exact name. Output charges. Okay. Also, energy of output is also important when operating in the range of hard switching transition. So finally, we saw that for the line input and the line output, the E-mode is a little bit better than the cascode mode. But at the beginning, I think we are starting to test only cascode because E-mode is not yet available for sampling, let's say, test. What was interesting also is to see that the neutral half-bridge leg have a, let's say, even with lower error-on device, there were not big difference, let's say, in switching losses. That is also the test that has been made on simulation more exactly, that has been made at 70 kilohertz and also at 100 kilohertz. And the E-mode is also almost the same losses in 140 compared to the cascode at 70 kilohertz. So my final conclusion will be that for our AC-AC converter, the GaN losses at 70 kilohertz cascode or 140 kilohertz E-mode is about half the IGBT losses we have today at 20 kilohertz. But in that simulation, there is no, let's say, inclusion of the magnetic losses. So we will have to evaluate what will be the losses on the magnetics. For the user, GaN implementation needs more AMC filter, introducing extra losses. So at least we need an order more. So we were with a 4 order, I mean two LC cell of filtering. Now we have 3, so we have to go to 6 order filtering order. And finally, GaN switching are still expensive compared to IGBT and MOS, but since the beginning of Google Challenge, the price has been lower, reduced to a factor of 10. And so with this factor of 10, today we still need about 5 ratio to be competitive with the actual IGBT. So that's it, short and strong.
Thank you, Paul. So, any question for Paul? What it was missing in your presentation was just to show a little bit how you were able to squeeze down with the different level, how
yes,
much.
I used to show it.
What it was interesting to say is that the expectation from the Google Challenge box was reducing 1/3 of the volume, but they were able to squeeze to 1/8. So it was they were well beyond the limits, but it was very good. Any question? Okay, please.
How did you choose the frequency of 140 kilohertz for the inverter?
The question is, how do you choose the 140 kilohertz for the inverter?
So it's a range of it's a range of frequency between 100 kilo to 400. 100 kilohertz, it's when you have full power. As you have to maintain the ZVS condition, we were to change this frequency. And in order to be able to reduce the size, the minimum frequency was 100 kilohertz. And maximum is coming with the minimum power, okay? So that's really, let's say, zero soft switching, let's say, constraint that has lead to that kind of frequency.
Okay. Any other question? Okay, if not, let's thanks Paul again.